In this video, we're looking at a straw containing fluid, just like you can pick up from any beverage. We put our finger or thumb over the top, and we trap some air in here. That air is clearly lower pressure than the air outside at atmospheric pressure, and that's what's holding this fluid in place. We have a difference in pressure between the top and bottom, and we want to know how low is that pressure. If this height here is, we're asked for 10 centimeters. So that's 0.1 meters. We're told that the density of the fluid, here this Greek letter rho, is 1,000 kilograms per cubic meter. And the atmospheric pressure is 101,300 pascals. Remember, a pascal is a Newton per square meter. And we want to know what is this pressure up here. So we begin by making a free body diagram to account for the forces on this column of fluid. Here's the column of fluid. Not exactly a free body diagram. I've drawn a bit more detail here than I need to, but I know pushing up on the fluid, let's actually stick with a dot. Pushing up on the fluid, so from below, is the pressure, P0, times the area of the straw, A. We're going to call this area A. We have the freedom to do that. I can choose what that area will be, and we'll see if it has any effect on the dynamics of this problem. What is pulling down? Well, I know not pulling, but pushing, because it's pressure, not pull here. I have the pressure up here times the area. Notice P0 is atmospheric pressure. P, with no annotation, is the pressure in the air above. And what else? This is not massless water. It has another force here, the weight. So that weight is the mass of the water times g. So now we can use Newton's second law. I know that the sum of forces in the y direction, the vertical direction here, is going to be equal to the mass times the acceleration. But in this case of statics, of force balance, the acceleration we seek is 0. So the sum of forces will equal 0. Now we can use our free body diagram. The way I use a free body diagram is by reading it in the direction I care about and accounting for these forces, positive being up, negative being down. So we're saying that P0 times A minus P times A minus mg equals 0. Now, how do I figure out this m? Well, I know that mass is related to density. What is density? It's equal to the mass divided by the volume. So that means mass is density times volume. So mass will be that density, remember we're using the Greek letter rho here, times the volume. Now what is the volume of the cylinder? It is the height of the cylinder times the cross-sectional area. So rho AH. That is the mass. Bringing that into our equation here, I have P0 still, times the area, minus PA, minus mg, which we see is rho g h a. I've got my a as the final factor everywhere there, so you might guess what's coming. If I have an a in every term, as long as a isn't 0, I can divide both sides by a. So I see, although I chose a symbol for the area, it actually affects all these terms in a linear fashion. It's multiplied one factor there, so we can eliminate the influence of a, which is a fortunate thing. So P0 minus PA, P0 minus P, the difference in pressure, is equal to, I see, rho GH. What are the units of each of these things? Well, you can tell from the symbol. This is a pressure, this is a pressure, so these have dimension of pascals, force per unit area. And here we have also, this must represent a pressure. So that is, looking at the units here, mass per let's use the SI symbols, kilograms per cubic meter. G has units of meters per second squared, and H has units of meters. I know that a kilogram meter per second squared, that's MA, that must be a Newton. So I see newtons here. And we have a meter over meter squared, so that's a square meter. So we've confirmed the right-hand side here also has units of pressure, all three of these terms. Now, what are we actually looking for? We're looking for P, the pressure, and it will be a function of the height of the column of fluid. So let's solve for P. I'm just going to subtract rho GH from both sides and add P to both sides. Then I've got P by itself, so I can see that the pressure is equal to atmospheric pressure minus rho GH. So what does that predict? If H were 0, we can check the limiting case of no fluid. I'm going to be subtracting nothing from atmospheric pressure, and that makes sense to me. That would mean there's no fluid in the straw other than the air itself, and of course that'll be at atmospheric pressure throughout. But we see the taller the column of fluid is, this H here, the more we're going to drop the pressure in the top there in order to support that fluid. Could I decrease the pressure without somehow having the water fall a little bit? In general, no. The way this vacuum lower pressure relative to atmospheric develops is a drop of water will fall out when you first pick up the fluid, and that displacement of this interface is what lowers the pressure up there. So that's pressure as a function of height. Let's see what the actual numbers are. That pressure will be atmospheric pressure here, which is 101,300 in general on a typical day, pascals, 101.3 kilopascals, minus the density of water is 1,000 kilograms per cubic meter, times 10 meters per second squared, and we were asked specifically about 0.1 meters of water in the straw. So a tenth times 10 times a tenth gives me a 1. So we're subtracting 1,000 pascals here. That tells me that the pressure in this straw is going to be 100,300 pascals. So how much of an atmosphere do I lose from every 10 centimeters of fluid? I can see the drop in pressure here will be about 1%. I have about 101,000 pascals, and I'm losing 1,000 pascals for every 10 centimeters of water. That means if I'm losing 1% for 10 centimeters, we will drop a tenth of an atmosphere, tenth of atmospheric pressure, for every meter of fluid that's supported. That clearly relates to the tallest we could make the straw. If I drop a tenth of an atmosphere for every meter of fluid, if I had 10 meters of fluid, the pressure up here would have to be 0 or a perfect vacuum, which would make cavitation happen, and we would have boiling happening at the top of this water, even at room temperature. So I hope that's a helpful explanation of question 1 in this introduction to pressure.